Welcome to AI Paper Podcasts. Today we are looking at a paper that might just fundamentally change how you think about self-attention.
Yeah, this one's a big deal.
It is titled, You Need Better Attention Priors, coming out of Stanford University by Elon Littman and Gabe Guel.
This is a heavy hitter. It's proposing a new mechanism called just HOAT that's Generalized Optimal Transport Attention.
And look, if you are an engineer who's been frustrated with context length limits or, those weird stability issues.
Where your model just collapses?
Yeah, where it just collapses. You really need to pay attention to this one.
Absolutely.
So let's do the 1-minute executive summary, maybe for the engineers in the back. What is the core problem here, and what is GOAT doing differently?
Okay, so the problem is that standard self-attention, the dot product plus softmax we all know, it really struggles with length extrapolation.
Right.
It also develops these attention sinks where the model just dumps a ton of probability mass on the first token to satisfy the softmax function.
And the current fixes like RoPE or ALiBi.
Sure. They're essentially heuristics. I mean, they patch the problem, but they do it by entangling position with the semantic content.
And GOAT, what's the new idea?
GOAT reframes the entire attention mechanism through the lens of Entropic Optimal Transport, or EOT.
Okay.
And the authors prove that standard attention mathematically implies you are assuming a uniform prior distribution over your sequence.
Which is a bad assumption.
A very bad assumption.
Yeah.
So GOAT replaces that uniform assumption with a learnable continuous prior.
And the result of that change?
It completely decouples the structural biases, like where a token is, from the semantic content, what a token actually means.
That's a huge claim.
And it allows for repulsive attention patterns. It handles infinite context extrapolation way better than RoPE. And crucially, it is fully compatible with FlashAttention kernels.
Without needing to materialize those massive quadratic bias matrices.
Exactly. No custom kernels.
Okay, that is a big claim. Standard attention implies a uniform prior. Let's really unpack that. I think most of us, we just view attention as a similarity search,
Right.
You have a query, you have keys, you do a dot product, find the best match. Why do the authors say this is flawed from a math perspective?
Right. So Littman and Guo ask us to shift our mental model. Instead of just similarity, you should view attention as an optimal transport problem.
An optimal transport problem.
Yeah, imagine your query token is holding a unit of mass, specifically a Dirac delta function. It needs to transport this mass to all the key tokens.
Okay, like a delivery truck trying to offload packages to different houses.
Exactly. Now, in optimal transport, you have a cost function. Here, the transport cost is just the negative affinity, basically how dissimilar the query and key are.
And you want to minimize that cost.
You want to minimize it. But standard attention also includes a regularizer. Use the softmax function, which corresponds to Shannon entropy regularization.
We use Shannon entropy to keep the distribution smooth, right? So it's not just a hard argmax.
Correct. But here's the aha moment from the paper. Maximizing Shannon entropy is mathematically identical to minimizing the KL divergence against a uniform distribution.
Oh, wow. So by using standard softmax, we are implicitly telling the model, unless the data screams otherwise, you should attend to everyone equally.
Precisely. The model effectively penalizes any deviation from a totally flat uniform distribution. So the model has to literally fight this implicit uniform prior to learn any kind of structure.
Like, pay attention to the word right before me.
Exactly.
Yeah.
That becomes a fight against the default.
So GA generalizes this.
Right. Hence the name Generalized Optimal Transport Attention. They replace that hidden uniform prior with an explicit learnable prior, which they call pi.
So the new formula isn't just softmax of the scores,
It becomes the softmax of the scores plus the log of this prior.
which computationally just looks like an additive bias.
It does. But because it's derived from these first principles, it behaves very differently than just, slapping a bias on top.
So the structure of the sequence is handled by the prior.
And the meaning is handled by the dot product. They aren't fighting each other anymore.
This sounds like we were finally admitting that tokens have locations. And those locations matter completely independently of what the token actually is.
You got it. I mean, think about how much model capacity is wasted just trying to figure out, I should probably look at the previous token.
With a uniform prior, it has to learn semantic features that are proxies for previousness.
Right. With GOAT, the prior just says, hey, looking at the previous token is a pretty good default. And the semantic attention only kicks in if there's a specific reason to look somewhere else.
This leads us directly to the attention sink phenomenon. This has been a really hot topic recently.
Yeah, the sync token.
We've seen these LLMs where if you look at the attention maps, huge amounts of probability mass go to the start of sentence token, even if it's completely irrelevant.
And we usually treat this as a quirk, like, oh, the model just needs somewhere to put its garbage probability.
But this paper argues that sinks are actually mathematically inevitable.
They are. And this is the EOT perspective again. Think about it. If your semantic signal, the dot product, is weak or low entropy.
The model is confused.
Right, the model is confused, and the EOT objective forces the distribution to collapse back to the prior.
Okay.
But remember, in standard attention, the prior is uniform. It's flat. So when the model is confused, it wants to spread attention everywhere, but that's high entropy, which might be bad for prediction.
So to create a sink, it has to hack the content.
Exactly, hacking the content.
What does that mean, hacking the content? It changes the vector itself.
Yes. The authors call this a content sink. To create a sink in a standard transformer, the model learns a massive norm for the key vector of that first token.
It makes that first token scream mathematically.
Just to override the uniform prior. Yeah.
That sounds incredibly destructive. You're corrupting the semantic meaning of your first token just to serve a structural purpose.
It is destructive. It entangles the where, the what. So Joad introduces what they call a prior sink.
Okay.
They explicitly add a learnable term, let's call it UJ, which is a key-only bias.
So the model can just learn, hey, token 0 has a high UJ score, no content needed.
Exactly. It creates this margin in the log prior. They actually have a theorem for this. Theorem 5.1, collapse to prior.
And what does that prove?
It proves that as the signal strength from the content goes to 0, the attention explicitly reverts to this learned prior.
So when the model has nothing to say, it defaults to the sink that's defined in the prior, leaving the content vectors completely alone.
And that stability is totally decoupled from sequence length. You don't need to see 100,000 tokens in training to know that the sing is at position 0.
That's a huge deal for stability. But I want to get into the gears of this. We're talking about learnable priors.
Right.
Usually when I hear learnable bias in attention, I immediately think of a bias matrix of size L by L.
Which is a complete non-starter.
Right. If I have a sequence length of 100,000, I cannot materialize a 100,000 by 100,000 matrix. I'll run out of VRAM instantly.
Of course.
So how does GOAT implement this efficient learnable prior without blowing up all my memory?
This is really the engineering elegance of the paper. They parameterize the log prior, this KIJ term, and they break it down into two main components. First, there's the relative position component.
And this handles things like look at the previous token or look 5 tokens back.
Exactly. They use a spectral decomposition. Essentially, it's a truncated Fourier series to model these shift invariant relationships. But there is a really clever twist here compared to things like RoPE or linear attention.
What's the twist?
Because Joe operates in log space. Remember, we're adding to the logits before softmax. The spectral weights can be negative.
Negative weights. Why does that matter so much?
Well, in standard kernel methods like linear attention, you're usually restricted to positive definite kernels. You can model attraction. I like tokens that are close to me.
But with negative weights in log space?
Jodes can learn repulsion.
Repulsion. So the model can explicitly learn to say, do not look at the token 3 steps back.
Exactly. It can suppress attention at specific distances. That's a level of expressivity you just don't get with standard positive definite kernels.
That is fascinating. So it's not just about pay attention to this, it's actively saying ignore that. It feels like it adds a sharper resolution to the whole attention mechanism.
It does. It gives the model a chisel instead of just a paintbrush.
Okay, so we have the spectral component for relative position, and we also have the sync term we mentioned, the UJ.
Which is modeled as just a simple MLP over sinusoidal inputs. It's very, very lightweight.
But wait, we still have to add this to the dot product? If I'm using FlashAttention, I can't just inject a custom bias matrix in the middle of the CUDA kernel.
Right.
FlashAttention is strictly Q.K transpose. How do they get around this?
They use something they call a scaling trick. This is something engineers should really look at. They modify the query and key vectors before they even hit the attention kernel.
Walk us through that. How does that work?
Okay, so imagine your head dimension is DH. They split that dimension. Most of it, say DAC, is for the content. A small slice, DTP, is reserved just for these prior components.
Okay, so we're just concatenating the prior information into the vectors themselves.
Yes. But here's the trick. Standard attention scales the dot product by 1 over the square root of D.
Right.
That dampens everything. But we want our prior to be stable and strong, right? So GOT scales the content part of the vector by a factor that cancels out the standard scaling.
So it's effectively applying a different temperature to the content versus the prior.
That's it. The effective temperature for the prior is 1. It's completely unscaled.
So they pad the vectors, inject the prior information into that padding, and they prescale it. So when FlashAttention runs its standard operation, the math just works out perfectly to be content score plus prior logic.
You've got it.
That is clever. So you can use FlashAttention 2 or 3 completely unmodified. You just feed it these composite vectors.
It's a drop-in replacement. No custom CUD kernels required.
That is the difference between a paper that stays a paper and a paper that gets into production, right? If I have to write a custom Triton kernel to use your method...
I'm probably not going to use it.
Exactly. But if I can just pad my tensors...
Yeah, then it's practical.
Okay, let's talk comparisons. The reigning champion of positional embeddings right now is RoPE, rotary positional embeddings. It's in Llama, it's in everything. How does GOAT stack up?
RoPE is great, but it has a fundamental flaw, which is entanglement. RoPE injects position multiplicatively through rotation.
Right.
That means the magnitude of your positional signal depends on the norm of your content vectors.
I see. So if my content vector is small, maybe it's a stop word or something low information, my positional signal also becomes weak.
Exactly. You can't have a strong positional bias with a weak content signal. They're coupled together.
But GUA is additive.
GUA is additive. The structural bias is completely independent of the semantic norms. So with GUAD, even if the content is complete noise, the model still knows exactly where it is in the sequence.
And that disentanglement is key for extrapolation.
It's everything for extrapolation.
What about ALiBi? That's the one that adds a static penalty based on distance.
ALiBi is actually a very close relative. The paper shows that ALiBi is essentially a special case of GOAT.
A special case how?
If you ask for the maximum entropy recency prior, which is basically the most generic assumption that more recent is better, you get ALiBi.
So ALiBi is just GOAT with a specific, fixed, non-learnable setting.
Right, but that means ALiBi is rigid. It forces a linear decay. GOAT is learnable. It can learn that linear decay if it needs to, but it can also learn complex periodic patterns or sinks, which ALiBi could never capture.
Okay, talk is cheap. Show me the curves. They ran experiments. The big one for me is length extrapolation. This is the holy grail. Train on short sequences, test on long ones.
It really is. So they used the C4 dataset. They trained on a context length of 2048. Then they just pushed it to see what happens.
And RoPE?
RoPE degrades catastrophically. At just 2 times the length, you see the perplexity shoot straight up. The model just gets completely confused.
And GOAT?
GOAT maintained low perplexity up to 16 times the length.
16?
16. That's over 30,000 tokens, despite never seeing anything longer than 2,000 during its training.
That is wild. 16x extrapolation without any fine-tuning.
Yes, because the prior is shift invariant and decoupled. The model learned the rules of position, not just the specific positions it saw in training. It's like learning the concept of yesterday instead of just memorizing the date.
They also did the needle in a haystack test, right?
They did. This is where you hide a passkey somewhere in a massive text and ask the model to retrieve it.
And what happened?
RoPE and the sinusoidal embeddings, they started failing as the needle moved deeper and deeper into the context. GOAT achieved near-perfect retrieval across all depths and all lengths.
There was also a really interesting experiment on genomics, DNA modeling.
This one fascinated me. They did next token prediction on the human genome. GOAT outperformed RoPE on validation loss, but the visual was what was so striking.
The visual?
They looked at the GC content profile. That's the ratio of G and C bases in the DNA.
Which has a very specific statistical structure in real DNA.
Exactly. The sequences that were generated by GOAT matched the ground truth GC profile with a Pearson correlation of 0.466. RoPE was way down at 0.320.
So RoPE was generating DNA that didn't quite look like real DNA statistically, whereas GOAT captured that underlying structural prior.
Yes, exactly. It's just GOAT actually learned the biological structure better, and then, just to show off, they applied it to vision transformers on ImageNet.
Images are 2D, though. Does the 1D logic even hold?
It does. They initialized GOAT with a uniform prior, so no 2D knowledge whatsoever. The model spontaneously learned a 2D center bias prior.
It figured out that pixels, the middle of an image, are usually more important.
All on its own. And this allowed for resolution extrapolation.
You mean training at a low resolution and testing at a high one?
Yes. Train at 224 pixels, test at high res. Standard vision transformers fail hard here because their position embeddings are absolute. JOT handled that resolution shift much, much better.
That result really drives home the generalized part of GOAT, doesn't it? It's not just for language, it's for any sequence data where structure matters.
Exactly. It just learns the geometry of the data.
So what does this all mean? We've got a model that treats attention as optimal transport, decouples the what from the where, and just crushes the state-of-the-art on extrapolation.
I think the big takeaway, especially for engineers, is that we need to stop treating positional encodings as these hacks or heuristics.
Right.
We've been trying to patch a hole in the math this whole time.
The whole being that implicit uniform prior.
That's the one. We've been using RoPE and ALiBi to fight the fact that our attention mechanism just assumes a flat universe. This paper suggests that if you fix the math, if you admit that attention is an optimal transport problem and give it a proper learnable prior, you don't need the hacks.
And you get the stability of attention sinks for free without smashing your content vectors.
Right. I mean, if you are building long context models right now, or if you're struggling with those weird stability issues where your model just collapses, JOT offers a drop-in replacement that is mathematically grounded. It's not just another trick. It's a correction to the theory.
It really feels like we are maturing from the alchemy phase of deep learning into the chemistry phase, actually understanding why these things work.
And that understanding leads to better, more efficient models.
Well, that wraps up our look at You Need Better Attention Priors. A massive shout out to Lippman and Goel for this work. It's dense, but it is so worth the read.
Absolutely.
For everyone listening, next time you stare at an attention map and you see that massive bar on the first token, remember?
Yeah.
It's not a bug, it's just your model begging for a better prior.
Give the model what it needs.
We'll catch you on the next paper.